Hello again. Now we are getting another expression for the stress, which is the stress is equal to minus my over I. How this is come? Due to the sagging moment which we have talked about, there is a force, there is a stress here in the upper portion which is compressive, accompanied by the stress in the lower portion which is tension. And if we take infinitesimal small area delta A, for which we applied the stress, then the resultant will be dF, which is a small force value, and we take moment of the forces. Here is a compression and there is a tension. At the end we are coming to that expression, for which the sigma is normal stress in the member, the moment, which is the resultant internal moment, and I is the moment of inertia, and Y is the distance or perpendicular distance from the neutral axis for the point for which we are evaluating the stress. Due to the bending moment in that case, which is causing sagging of the element, we have compressive stress above the neutral axis and tension stresses below the neutral axis. We come to an example. An aluminum rod with a semicircular cross-section of radius r equal to 12 mm is bent into the shape of circular arc with radius rho 2.5. Knowing that the flat face of the rod is turned towards the center of curvature of the arc, determine the maximum tensile and compressive stress of the rod. Use E as equal to 70 gigapascal. This is the section for which we have this semicircular cross section, and this is the R12 mm, and the flat portion, which is the lower one, is pointing toward the center of curvature, which means that it is subjected to hogging moment in this direction, because this portion will get expanded on the top and getting contracted or shortage at the lower portion, and this is the flat portion. The radius of curvature is giving us as rho equal to 2.5, so from the neutral axis to that point is 2.5 and 2.5, and this is the shape before application of the bending moment. It will be hooked like that. In order to get the expression, we want this section is not rectangular section, so first we have to determine the CG distance, which is equal to y bar, and by use of the relations of the areas, and we can estimate that y bar is equal to 4r over 3 pi. R is 12, we multiply 4 by 12 divided by 3 pi, we get 5.093, which constitutes the distance. In order to get the maximum strain, knowing that at the lower portion, which is flat, we have maximum compressive, and in the upper portion, which is circular, we have tensile, so the maximum strain is equal from the first expression that we have C over R. C is 12 minus y bar minus 5.093 divided by 2500. This is the positive portion, that one, while for the negative one, the flat one, it will be equal to minus y over r. This is the y, 5.0093 divided by 2500, which is the radius. We get here the strain in the lower portion, flat portion. For the stress, we multiply by the modulus, Young's modulus for the CC 70, so we can get, in order to get the positive value, we multiply this strain by 70 gigapascal. We are coming to 193.40, and for the stress of the negative portion, the lower portion, we multiply the strain 2.0372 10 to the power of minus 3 by 70 gigapascal, we get 142.6. This negative sign indicates that this is compressive, while for the upper portion is being positive. Here we have example. We have this section which is subjected to bending moment of 1850 Newton meter. It is required to estimate the bending moment. We can see that this moment here is sagging, which will cause compressive stress in the upper portion and tension stress in the lower portion. In order to get the stress, we have direct relation, which is F equal to my over I. We want to get the inertia of this section. In order to get the inertia of this section, we have to estimate the Y bar. It is we divide into two areas, which is the first area is 2 by 6, while the other area is 6 by 2. And in order to get Y bar, we are saying A1 Y1 plus A2 Y2 divided by the addition of the two areas, summation. So 2 by 6, and if we take that as ordinate, we are saying 2 by 6 multiplied by the distance from the CG of the first area, 3 plus 2 multiplied by 5, and here the area is 6 by 2 multiplied by 1 divided by the addition of the two areas, which is 2 by 6 plus 2 by 6 by 24. We get this Y measured from here at 3 cm. So this is the CG distance is 3 cm from here, and the remaining distance will be 5. This is the location of the neutral X from which we can proceed and evaluate the stress, compressive stress and positive stress. So the maximum value, we can consider this compressive strength my over I. The moment is 1850, Y becoming 5, as you can see. Next step, we need to evaluate the inertia. The inertia of that section is equal to the inertia for every area plus the multiplication of the area by the square distance from CG of each area to the neutral X distance. So we have here 2 by 6 to the power of 3, 2 by 6 to the 3 divided by 12 plus the area 2 by 6 multiplied by 5, this is here, minus 3 square, and here also the parallel is 6 multiplied by the perpendicular to the power of 3 divided by 12 plus the area is 12 by the distance from CG. Here our CG point is at 1.5 while the other one is 3, so the square of the area, the square of the distance is 3 minus 1.5, which is 1.5, 3 minus 1 to the square. We come to the end that the inertia value is 136 to 10 over 4 millimeter square. So direct substitution, M 1850 Newton by 1000 because by 50 divided by the inertia 136 by 10,000 will come that the stress is 68.014 megapascal. Thanks a lot and see you next time.